let's look at functions. Let's look at functions. Let's look at functions. We have done relations on our previous tutorial and sets. So now we are going to do functions. So I need a highlighter. I get this one. Right, the green one. Okay, so by the end of this unit, you should be able to describe the concept of functions, represent the functions by using graphical representation, as well as be able to identify different types of functions. That's what matters here. That's what matters here. So let's look at what we call functions. So a definition of a function is a function f from x to y is a relation from x to y having the following properties. Guys, let's make sure that we are always on what? On mute. Let's make sure that we are always on mute. So the properties are that the first thing is that the domain of f is what? Is x. That's the first thing. Our domain is x. Then the second thing is that if xy and x prime and xy prime are element of this function f, then y must be always equal to y prime. What it means is that whenever you've got this x mapping to something y, it's obvious that whenever you have that x again mapped to something, that something must be always equal to this y, because you must not have a single value in the domain giving us different values in the range. So a function from x to y is sometimes denoted by f, such that x mapped to what? To y, where our x, where this y is an image of x. So if you look at this one, at this diagram, which shows this one, our x as the domain, and then this one as the range. If you look at that, from this domain, we've got one arrow from this y, from this one going to A, and then this arrow going here, and then this arrow going here. So if you look at that, it means that, okay, I just want to add someone as in the copy button. So if you look at that, if you look at this here, you've got a value here mapping to a single value. There is no way you are going to have one value mapping to more than one value. So that's what we call a function. So the domain of f is x, and the range of f is also a, b. So the range of a relation R is the set y is an element of y, such that xy is an element of R, or some x is an element of x. So if you look at this, this is our domain and this is our range. That's what we are talking about. So for example, the relation is represented as f of x is equals to x squared. So this relation is a function, and the domain is the set of all real numbers. Okay. So this relation is a function, and this and the domain is just the set of all real numbers. Why? Because if you put any real number for x, you can always get the value of y. So the range of f is the set of all non-negative real numbers. Why? Because if you put any value that you put for x, the result that you are going to get is always positive. So in other words, the range is all non-negative, because if you square any negative number, will give you a positive number. So if f is a function, f such that x maps to y, given a value in set x, we can obtain the value in set y. So this process is called function application. So you can apply the function, given an example as follows. If you put f of 2 here, it means for x you are putting a 2, which will become 2 squared, and you get a 4. If you put f of 8, it will become 8 squared, and you get your range is what? Is 64. So that's how you can apply a function to any input. So example again, which of the relations define functions? So we are saying on these relations that we have, which one is defining a function from x to what to y? So what are we going to look at? At this relation, we've got 2, 4, and 4, 1. And then you've got 2, 4. So which means this value is for x, and this value is for y. This value is for x, and this value is for y. It's just the same as this relation on R2, where we've got 2, 4, 4, 1, 4, 2, 5, 6, as well as on R3. So if you look at the solution here, we are looking at A, which is at R1 first. We are saying this one is not a function. Why? Because 5 is an element of X. If you look at it, 5 is part of the domain, but it does not appear on these ordered elements, which means we do not have a 5 mapped to something. So whenever you have such scenario where you can have a member of a domain which is not having a corresponding value in the range, it means that relation cannot qualify to be a function. Why? Because for every input, you must get a result for that function. So if you look at R2, it's not also a function because the ordered pairs 4, 1 and 4, 2 have the same first element, but different second elements. So it's not a function. Why? Because you are putting a single value, but you're getting many values. So you need to get the exact value if you put if you put an input in a function. Also, R3, if you look at it, defines a function because it satisfies both the condition of the function, that is every element of x is the first element of some ordered pair, and there is no pair which is the same first order pair but different second order. So if you look at R3, we've got these two, and then this 4 is being here mapped to this range, and then we've got 5, this 5 mapped to something here. So that's the definition of a function. And then on the issue of drawing the graph, the functions of graphs, we are not going to waste much of our time. We've done this before at O level, A level. Those who didn't do A level, we've done this before at O level. We've asked you to draw a function of any given expression. It's just the same. That's the same idea. So the graph of a function, let f be a real valued function of a real variable, that is f maps r. F is such that r maps to r. So the graph of f is the set of all points x, y in the Cartesian coordinate plane, with the property that x is in the domain of f and y is equal to f of x. So we have to draw the graph of the function f given by the relation y equals x squared in order to draw the graph. In order to draw the graph of the function, we first take some elements from the domain, and then we see the image of them, and then we plot the graph. So what you are supposed to do is you can just pick a handful number of what? Of the values in the domain, and then you find the corresponding numbers in the range, the corresponding values in the range. And then from there, you can plot those numbers, and then you can join the graph. So if you look at this, they've just take -3, -2, -1 is 0, then 1, 2, 3 as the values in the domain, and then they plug them in your function, and then you got the what? The result within the range, which is -3. If you put -3, it will become -3 squared, and then you get a 9, then -2 squared, then you get a 4, -1 squared, you get a 1, 0 squared is 0, then 1 squared is 1, 2 squared is 4, and then 3 squared is what? Is a 9. Then you plot these pairs. That's why you see here we've got -1 and 1, 1 and 1, 0 and 0, 2 and 4, and then you join what? Join the graph. So this is what constitutes the what? The graph of this function. So that's how you can draw the graph of this function. Maybe what is important for this topic, what you need to know and what you need to remember are the types of functions. This is what you need to know, the types of functions. We've got 3 types of functions. So I think I need to add someone. Okay, so we have got the injective, surjective, and bijective as three types of functions. So let's look at the definition of an injective function. So a function f from x to y is said to be 1 to 1, or an injective function if for each every y is an element of y, there's at most one x is an element of x with f of x is equal to y. So that's what we call an injective. Take note of this at most, which is less than or equal to 1. So the condition given in the definition above for a function to be 1 to 1 is equivalent to if x and x prime are elements of x, and for f of x is equals to f of x prime, then x and x prime must be equal. So in other words, we are saying if you've got these two distinct values within your domain, if you put this in your function and you put this in your function, if it happens that you are going to get the same value, then it means that for this function to be an injective, it means this x and x prime, they are equal. So in other words, we are just saying this is A and this is B. And if you put them in your function, if it happens that they give you the same value or the same output in your domain, it means that those values must be equal so that the function can be what can be an injective function. So if a function from x to y is 1 to 1 and each element in y in its arrow diagram, we have at most one arrow pointing to it. So if you look at this one, you can say it's a one-to-one relationship or it's an injective. Why? Because if you look at this, here we've got only one arrow coming from this side, and here we've got only one arrow coming from this side, and here we've got one arrow coming from this side. And therefore, some of the values within the range, but there's no there's no value which is mapping to that. So this is an injective. This is an injective. Take a note of this scenario where you can have some values within the range but not being mapped by any value from the domain. We're going to talk about that when you talk about surjective function. So this is an injective function. If you look at it, we've got 1b, 3a, and 2c, which is a function from the domain 1, 2, 3, which is x, and then the range is 1, which is a, b, c, d. That's why I've got this x and y, and the function is here. And then you belong 1 and b, that's why there's 1 to b, and then 3a, 3 to a, and then 2c, which is from 2 to c. So this one is a 1 to 1 because for every single value that we're going to put as input to this function, we are going to get exactly one output value, just like that. So this is a graph which shows a one-to-one function. If you look at that, for every value that you put for x, you're going to get a single value for y. And if you try to do it here, you always get what? You always get two values here, which give you the same value of y. Minus 2, you get 4, and for 2, you get 4, just like that. So that's what we call an injective function. I don't know if there are questions there. Otherwise, we're going to look at what we call surjective function. So if f is a function from x to y, and the range of y of f is y, then f is said to be an onto y or a surjective function or a surjective function. So maybe guys, you can see the onto keyword, then you need to know that we are talking of a surjective function. You are talking of a surjective function. So the function from x to y is onto each element in y in its arrow diagram. We have at least one arrow pointing to it. We are saying at least, which is greater than or equal to 1. It's not always the case to have 2 arrows, 3 arrows pointing to a value in this range, but we are saying at least 1, which is greater than or equal to 1, which means maybe we can have different values here. Give us a single value on this side, on this one. It will be still a surjective function. So the function f, which is 1, A, which is 1 mapping to A, and then 2 mapping to C, and then 3 mapping to B. From X, which is this is our domain, and then our range Y is 1 to 1 and an onto, which is a what? It's a surjective. Why? Because if you look at the arrow diagram on the range side, we have got at least one arrow pointing to this one. And if you look at this scenario that I was talking about, whenever you've got a value here, which have got less than 1, like this one, if got 0 at arrow pointing to it, it means this one cannot qualify as a what? As a surjective function, So this is what we call an injective. You are saying at least 1, but for an injective, you are saying at most 1 arrow pointing to it. So this is the diagram, a graph of a function. F is onto if and only if every horizontal line intersects the graph in at least 1 point. This one, that's onto, that's an onto function. And if you look at it, that this the range that was twisted here, which is we are only taking positive real numbers. Then let's look at what we call a bijective or a one-to-one correspondence, which is this one, bijective, or a one-to-one correspondence. So definition, a function that is both one-to-one and onto is called a bijective function. So for it to be bijective, it means it must be injective as well as surjective. So how do you know that this satisfies both? That's what you need to master here, so that you know that this one is injective and this one is surjective. So we can say that this function is bijective. So if you look at this, the function f from x to y defined by the arrow diagram is both one-to-one and onto. Hence, it's a what? It's a bijective. How can we say that? By the standard of an injective, we are saying an injective is one-to-one, which means for every value that we give here, we must have a single output, a single value output. So if you look at it, for every value that we have here in the range, they've got only a single arrow coming from this side, right? Which shows that this is at most, because it's less than or equal to 1. And then if you go for a surjective, it says that we must have at least 1. And if you look at this one, it's always greater than or equal to 1 for the arrows which are here. So it means that this one is both injective and surjective. Hence, we can conclude that this function is bijective. So this is the graph. This is the graph for bijective. So a graph of a function f is bijective if and only if every horizontal line intersects the graph at exactly 1 point. So if you put in a horizontal line to cross the graph at exactly 1 point. So that's the bijective function. Then let's look at the inverse of a function. The inverse of a function is just the reverse of a function. I'm not going to ask you to prove it, but basically you just need to understand what is an inverse of a function. So in other words, for the function, we're mapping from x to y, and then for the inverse, we are now mapping from y back to what? Back to x. That's the inverse of a function. So let f be a one-to-one correspondence from the set A to the set B. So the inverse function of f is the function that assigns to an element B belong to B to the unique element A in A, such that f of A is equal to B. So the inverse function of f is denoted by f to the power minus 1. Hence, the inverse of B is equal to A, right? The inverse of f of B will be what? Will be A. If you look at here, you are putting in A to get a B. So for the inverse, if you now put a B, you must get an A, something like that. So if you look at that, you've got an A and a B, and you are saying A is equals to the inverse of f of B. It's just the same if you come here now, like here we are using this one is the arrow for the inverse, you are inverting back, and then this was the arrow going forward, where you are just saying f of A will always give you B. But now, sorry, but now when it is the inverse, you are going back, right? So if you say the inverse of f of B, then it will give you A, something like that. So that's the inverse of a function. That's the inverse of a function. If you look at this one, we've got G, this one, and then the inverse of it, we are now having this range participating as the domain here. If you look at it, it will become the domain, and then the domain will become the range. So here we're putting 1 and 2 to get an A, but now if you put 1, if you put an A, you get a 1 and a 2, and then if you put a C, you get a 3, just like what you're doing here, something like that. So the inverse of a function may not be a function. You need to note that. An inverse of a function sometimes may not be a function. If you look at here, we've got this sum of the element which are not part of the domain. So by that, this one is not what? It's not a function. So you need to note that. So it's not always the case when you can get an inverse of a function as a what? As a function. And then the inverse of an injective function may not be a function as well. Don't think it's necessary for this. But what you just need to know is just what you just need to know mostly is just these 3 types of functions and maybe some operations on a functions. Let's make sure that we are always on mute. Let's make sure that we're always on mute. Maybe what you need to get to understand also are the operations on a functions, operations on a functions, or the operations with the functions. So normally you can add, subtract, as well as multiply and divide functions. So you need to understand the terminology. When I say you say f of x plus g of x, what are we doing? If you are saying f of x times g of x, what are we doing? Something like that. So we can add 2 functions. So you might see this notation. You need to understand that you are adding 2 functions, which is f of x and g of x. So f plus g of x, it means that we are going to take f of x and then add it to what? To g of x. So here you'll be getting you take f of x. For example, what was our f of x? It was 2x plus 3, and then g of x, it was x squared. So I'm going to add these 2 things. That's why I've got 2x plus 3 plus x squared, where this one's g of x and this one is what? Is f of x. After that, you get x squared plus 2x plus 3. So just the same when you're doing multiplication, just the same when you're doing subtraction. Like you're saying f minus g at x, which means you're going to take f of x, which is this one, minus this one, and you are going to get this one minus that one, which is minus x squared plus 2x plus 3, just like that. For multiplication, it's just the same, guys. So you need to take note of where there is function composition and where there is function multiplication. If it is just a dot like this, you are multiplying. You are multiplying. So f at g at x, it means you're multiplying 2x plus 3 times x squared. That's why you're getting 2x squared, 2x cubed plus 3x squared, just like this. So for a division, it's just the same. We are just dividing. You are going to get 2x plus 3 over x squared, something like that. Then for function composition, it's now different from multiplying. It's now different from multiplying. Maybe let me just use this one. And it's not a dot, but it's just a circle like this. So this one is g of what? G of x. It's just what we call a function composition. So you are joining these 2 functions. So you're increasing their range. So function composition is applying one is applying one function to the results of another. That's what you call function composition. So when you're saying f of x of g of x, it means that you are putting the value, you are applying the output of f of x to g of x. So the result of f of x is sent through g of x, something like that. So if you have something like this, g of x of f of x, it means that you are applying f of x on g of x, something like that. So this one, for example, what do we get? You need to take this one and you put it on g of x, something like that. So if you look at it, it was supposed to be 2 plus we have what? We've got f of x equals 2x plus 3 and g of x is equals to x squared. To avoid confusion, let's call it input, which is our x is our input. So we are saying f of input is equals to 2 plus input plus 3. So whenever you have g and then you've got g of input, which is g of x equals to x squared or input squared. So whenever you have this expression, it's as good as you are putting f of x as input to what? To g of x. So what it means is that first you apply f of x, which is the 2 input plus 3, something like that, which is 2x plus 3, which is this one. And then after that, you apply that to g of what? To g of x, which is going to be 2x plus 3. Then you square it, both the input here that we have was x squared here. So you just put this and then you square. So whenever you have got a g of f of x, what it means is that you are going to take this value and you put it at x inside this g of x, which means we've got this x squared. So it is going to be 2x plus 3, then you square it, and then you expand it and you get the result. So that's how it differs from the multiplication. So this is the composition. This is the composition. Let's make sure that you are always on mute, unless if you want to ask something. Okay, so that's it, and that's all on functions. I don't know if I've got some questions on functions. Otherwise, I need to move on to the next chapter. So allow me to look at sequences. Allow me to look at sequences. It's very, very easy topic. It's a very, very easy unit. I know you can handle this on your own, but the fact that is part of your exam, I think it's good if I can pass through it. So there's what we call sequences and strings. There's what we call sequences and strings. I need a highlighter. So by the end of this unit, you should be able to describe the concept of sequences and operations of sequences, as well as discuss the concept of strings and operations on strings. So guys, let's look at a definition of a sequence. So a sequence whose smallest index is 1 is a function whose domain is either the set of all positive integers or a set of the form 1 up to n, which is n the maximum value for that. So if S is a sequence, we denote the first element as S1. This one is just S with a subscript 1, right? Something like this. And the second element is S2 with the 2 as a subscript, something like this, and so on. So in general, Sn denotes the nth element within your sequence. So you can have Sn, which gives you nth element within a sequence. When I say nth element, we are saying maybe it's the element at the first position, maybe at the 60th position, at the 20th position. So any nth element that you need in your sequence, you can get it through this Sn, right? So the ordered list 2, 4, 6 up to 2n is a sequence. So the first element is 2, and the second element is 4, and so on. So the nth element is given by 2n. And having this, you can actually find the nth element. So if we let S denote this sequence, we might have S1 is equal to 2, S2 is equal to 4, and S3 is equal to 6, and then Sn is equals to 2n. And then from there, maybe if you just want S1, if you put 1 for n here, you get 2. If you put 2, it means it's S2, you get a 4, something like that. So if you want S8, you just put an 8 here and you get a 16. So that's what you call sequences. So there's this one which says Munenzo buses charges $1 for the first kilometer and 50 cents for each additional kilometer. So for the first kilometers, if you are traveling with the Munenzo buses, you are going to be charged $1 for the first kilometer. Any additional kilometer, you're going to pay 50 cents for that. So in general, the cost, which is Cn, so with the subscript n, of traveling any kilometers. If you want a general formula that you can use to find, maybe if you're traveling 50 kilometers, 20 kilometers, what could be your charge, right? So it will be the cost of which is $1, the cost of the traveling the first kilometer, and then plus 50% times the number of n minus 1 of additional kilometers. So in other words, we are saying if you're traveling 30 kilometers, we are going to say $1 for the first kilometer, and then times 50 cents, then plus 50 cents times 29 kilometers, which is the remainder. That's why we put n minus 1, right? Where n is the number of kilometers. So we will be talking about, if it is 30 kilometers, we'll be talking about 30 minus 1, which is going to be 29. So the formula, or the nth element, the nth term, it will be 1 plus 0.5 times n minus 1. That's the formula that can give you. So this one, it's a sequence on its own. It's a sequence which can generate all the numbers within the sequence. So for example, you can have, if you are just traveling for 1 kilometer, you can have 1 plus 0.5 for 50 cents times 1 minus 1, which is going to give you a 0 on this side, on this part, which is going to give you $1, which means the cost of traveling 1 kilometer is just $1. And then the cost of traveling 5 kilometers, it will be just 50 cents times 4. And then you add $1 for the first kilometer, which is going to give you $3. So the list of fares in this example above is in a sequence, and the sequence can have also some repetitions there. So there are decreasing sequence and increasing sequence. I think it's just simple logic. If it is a decreasing sequence, just starting maybe from higher numbers going down, and then if it is an increasing sequence, you're starting from less numbers going upwards. Maybe it's 2, 4, 6 going upwards, ever increasing. That's an increasing sequence. It means the preceding is always less than all those which are following. So that's the increasing sequence. But if it is the decreasing, it means the preceding element or term within that sequence is always greater than the one which is following. So it will be keeping on decreasing. So a sequence is S is increasing if Sn is always less than or equal to Sn plus 1 for On. For example, 2, 4, 6, this one, you can call it, it's an increasing. Why? Because if you look at 2, is always less than all things which are going to follow up. And this one, 3, 5, 5, 7, 7, 8, what, is also an increasing sequence. Why? Because this 3 is always less than, and 5 is always less than or equal to everything that follows later. So a decreasing sequence is now a vice versa. You are starting from higher going down. So that's what you call a decreasing sequence. And then there's a subsequence now. A subsequence is when you take part of a sequence and make it a sequence on its own. So it's a subsequence. So let Sn be a sequence defined where n is equals to m, then m plus 1, up to any at the term. So let N1 and N2 be an increasing sequence satisfying Nk, and then Nk plus 1 for all k whose values are in set of M, then M plus 1. We call this sequence Snk, which is a subsequence of Sn. So the subsequence BC is a sequence of it's a subsequence of the sequence A, B, C, then Q. If you look at it, I think this one is not supposed to be there. is the subsequence of the sequence A, B, C, Q. And then if you look at it, you are going to take only this one. So BC will be a subsequence of this sequence. So notice that the sequence CB is not subsequence of the sequence. It's as good as this one. The sequence 2, 4, 8, 16 is a subsequence of the sequence 2, 4, 6, 8, 10, 12, 14, 16, just like that. But you cannot have maybe 6, 4, 2 as a subsequence of it, but it will be 2, 4, 6 just going upwards as a subsequence of that sequence. So now let's look at some sequence operation where you want to add this sequence. So if you look at that, we have got this one, which is this one is what? Oh, okay, this was general formula for a subsequence. So if you want to do a sum and the product of sequences, if you want to do a sum and the product of sequences, you can use this. The summation from I is equals to M up to N. So if you look at that, the summation, you'll be adding each and every element within the sequence. So if it is 2, 4, 6, 8, you'll be adding 2 plus 4 plus 6 plus 8, just like that. So that's how you add the elements or the terms of a what of a sequence. You just add them. Here I've got AM plus 1 plus up to AN. So you'll be adding them as they come. And then for the product, you just multiply them. If the sequence is 2, 4, 6, just multiply 2 times 4 times 6. That's how you do multiplication for sequences. That's what I think I need to add someone. So that's how you do operations with the sequence. And this one was an example when you have a sequence which is 2, 4, 6. Okay, this one, it was a general sequence. We've got A1 plus A2 up to A3. Why do we have that? Because we have from I is equals to 1 up to the maximum, which is I is equal to 3, right? So maybe there's something what I've skipped here. We are saying let a sequence be defined by AN, which is this N is a subscript of N, of A. So it's A and then an N here, where N is there for the N and the term, which means you're going, if you want the first term, you just put a 1 here. So we are saying it is equals to 2N for N is greater than or equal to 1. Then if you want to find the summation of this A, the summation of AI from I is equals to 1 up to I is equal to 3, it means you are going to take the first 3 terms of your sequence. And the first 3 terms, which are the first 3 terms, which is it's A1 plus A2 plus A3. And if you put a 1 here, it means you are going to have 2 times 1 for N. So you are going to have a 2. And then if you put a 2 here for this A2, you are going to have 2 times 2, which is going to give you a 4. And then the next one is 6. And then you add both of them, you get a 12. That's how you work with these sequences. And then you can do the same for multiplication, and you get 2 times 4 times 6 to get a what? To get a 48. So this is just some, I think this is another example again. The sequence is defined by the rule AN is equals 2 times minus 1 to the power N, where N is always greater than 1, right? So find a formula for the sequence S defined by the summation Sn is equals to, Sn is equals to the summation from I is equal to 0. The summation of 2 times minus 1 to the power I from I is equal to 0 up to N. So if you look at this one, what are we doing here is that we are going to start from I is equal to 0 and then up to N, until this I is equal to N. So if you look at that, we are supposed to start because our N here is always greater than what? Our N is always greater than 1, is supposed to be greater than 1. So if you put our N is always greater than 1. So if you put our I is 0 there, what are we going to get? If you put our I as 0 there, it's not going to work that way. So you're going to have 2 minus 1, 2 times minus 1 to the power 1 plus 2 times minus 1 to the power 2 plus 2 times minus 1 up to 2 to the power minus 1. So 2 times minus 1 to the power n. And then if you look at that, this one is going to give you 2 minus 2 plus 2. And then the next one will become minus 2, the next one. So it's as good as this one will be cancelling 2 minus 2, give you a 0, and then 2 minus 2. So it means that every the first and the second element will be always cancelling each other, will be always cancelling each other. And then what is going to give you is going to give you a 0. Otherwise, it is going to give you a minus 2 whenever n is what? Is odd. So if n is even, you are going to get a 0. And when n is odd, you are going to get a minus 2 for this one. And then let's look at a what? At a string. Let's look at a string. Normally on strings, what I want you to understand is a string concatenation and nothing else, the way of joining strings. And then on sequences, maybe what I want you to understand on sequences is just the basic of addition of and multiplication of sequences. Maybe if there's something, I will tell you what I want you to do. So a string over X is a finite sequence of elements from X. So let's, for example, let X be ABC, right? If we let Q1 be equal to B and Q2 be A and Q3 be A and Q4 B C. So we obtain a string over X. So you are making a string out of this set. So you can make a string over X. So this string is written as BAAC, where we are having Q1, Q2, Q3, something like this. So the sequence or the string will become BAAC, something like this. That will be your string over X. So in other words, you can make any string from this X that you have, and you can even repeat the letters. So the definition, we let X with this star denotes the string of all strings over X. So this one is a set of all possible strings that you can make over the set X, including the now string. The now string is an empty string. And we let X plus denotes the set of all non-now strings over X. So if we are saying we want X plus, it means that we want all the possible strings that we can generate from that given set, excluding the now string, right? So the string with no elements is called the now string and is normally represented by this lambda. For example, if you have got A, B, you can make some strings or some elements in X star, which is all the possible strings that we can make. The first one is the empty or the now set, the now string. And then after that, you can have either A as the string and then B, or you can have AB, or you can have BAA, or you can have AAB, or you can have this B to the power 20 and A to the power 5. What it means is that it's a repetition of B's 20 times and A's 5 times, and then, excuse me, then you can have a B and an A. So the length of a string, which is normally represented by alpha, is the number of elements within that string. So the element of the length of a string alpha is the number of elements in that string alpha. So the length of this alpha is denoted by the modulus of alpha. So if you are being asked of something like this, you are being asked to count the number of elements that makes up that string. So if you are having this, I think this one, maybe it was part of your assignment. It was just here in this slide. So if you look at this, you've got this alpha, which is AA, BAB, and then beta, A to the power 3, B to the power 4, and A to the power 32. Then the modulus of this one, you need to count. We've got 1, 2, 3, 4, 5. So this is the length of this string. And then the length of this one, if you look at this, we've got a to the power 3, so this is 3. Then b to the power 4, so 3 plus 4 to make it 7. And then a to the power 32, you add 7 plus 32 to get 39. So if alpha and beta are two strings, the string consists of alpha followed by beta can be written as A is alpha beta. So this one we call it string concatenation. So how do you do string concatenation? So for example, if you are given T with AAB and E with the CABD, then if you're supposed to find the concatenation of T and E, you just need to append CABD to the end of the string T. So you have got AAB, which is this one for T, and then you've got the CABD, this one, which is for what? For E. So that's how you concatenate them. You do not need to do any multiplication whatsoever. So if you look at ET, just need to make sure that you put E first, which is CABD, and then after that, you put the AAB, which is the T. So if it is T times alpha, which is you know that this one, the lambda, this one is in a now string, which means it's T concatenate with nothing, which is going to give you T, just the same as now string concatenating it with the T. So you're going to get an AAB. So that's all on string sequences and the strings. Maybe what I want you to do is to go and look on the other part of strings, of sequences, which is the arithmetic progression and the geometric progression. I'm finding out that I didn't include those notes on these slides, which means that maybe I need to find maybe to save time. What you can do is go and look at arithmetic progression and go and look at arithmetic progression and geometric progression. On arithmetic progression, please do the nth term and the summation of arithmetic progression, and for geometric progression, do the same. The nth term as well as the summation of terms of geometric progression. Please go and look at that. If you have any challenges, if you look at our previous video, for the guys that have done with on previous semesters, they on our YouTube, if you check on that, I'm sure you can find that portion where we're doing sequences, and we have covered that. Or you can just ask me, I can also help you. Maybe what we need to look at is now the propositional logic. Yes, I'm sure we are still within the time. And after propositional logic, for predicates, I'm going to do the same, guys. For predicates, I'm going to share a video with you where you can follow. There's a video on the predicates. I've done a video, the one which is already pre-recorded. I will share with you. It's already there on our YouTube channel. I just share with you. Maybe you'll be not able to locate it. And then after that, I'll be always there to assist if there is any challenge. I'll be always there to assist. So guys, let's look at this. Let's look at logic. This is also a very, very important topic for your module. So by the end of this unit, you should be able to explain the concept of propositions, apply operations on propositions by using what we call the truth tables. So that's all for this one. So the introduction: in developing a mathematical theory, assertions or statements are made. So these statements are made in the form of sentences using words and mathematical symbols. So when proving a theory, a mathematician always use a system of logic where you need to know that from this step we go to this step and you go to this step. So this is also the case when developing an algorithm for a program or a system of programs in computer science. So the system of logic is applied to decide if statement follows from or is logical consequence of or one or more statements, right? So let's look at what we call a logic, what we call logic. So logic is the study of the principles and the methods that distinguish between a valid and invalid argument. So logic is the basis of all mathematical reasoning and of all automated reasoning. It has practical applications like designing of computing machines to the specific of systems, the specification of systems to artificial intelligence. You can apply to computer programming and a lot. So let's look at what we call a statement. This what we call a statement. These are the basics of logic, and you need to really understand these basics. So when you're looking at a statement, is an assertion or a declarative sentence that is either true or false, but not both. So what you call a statement is something which is either false or true, but it cannot be both. So that's what you call a statement. And then a statement is also referred to as a proposition. So if you heard someone talking about propositional logic, we are talking about statements. And these statements must have one single truth value. It can be either true or false. So the truth table, the truth value of a mathematical statement can be determined by application of known rules or axioms and laws of mathematics. So a statement which is true requires a proof. For example, if you say 2 plus 2 is equal to 4, is it true or not? It is Sunday today, is it true or not? So if a proposition is true, we can say its truth value is true. But if a proposition is false, we can say its truth value is false. So the truth value true and false are respectively denoted by the letters T and F, or by 1 and 0 respectively. So normally when you're drawing the truth tables, these are things that you are going to find. You're going to find either T or of F, which is true or false, or you can find a 1 and a 0, which is false. But for this mode, you're just using a T and F. You're just using a T and F. So a symbol or a primitive, let's look at a simple statement. So guys, here we are just saying there's what we call a statement, and we have said that a statement is an assertion or a declarative sentence that is either true or false, but not both. But take note that this is just a general statement, but you can have what you call a simple statement. It means it's still a statement, but this one, it have got some of its own form. So a simple or a primitive statement is a statement which cannot be broken down into anything simpler. So it means that it is in its simplest terms. So a simple statement is denoted by use of letters like P, Q, R, those small letters of the alphabet. And normally we use P, Q, R to denote the simple statements. For example, we can say there are 7 days in a week. So if you look at this, we can denote it by P. So P is such that the statement P is such that there are 7 days in a week, just like that. Okay, so we can also have so we present P is a simple statement here. So we can have another simple statement R, which will be saying that 3 plus 2 is equal to 6. Don't worry, you know that 3 plus 2 is not equal to 6. So which means this statement, its truth value is false. Because we can prove that 3 plus 2 is not equal to 6. So R is a simple statement because it is in its simplest form. There is no way you can break down this statement into other simpler terms. So you need also to understand those statements that can be propositions and those that cannot be propositions, right? We need to understand those that we can say this one is a statement, this one's not a statement. If we say grass is green, yes, this one you've got either truth value of either true or false, because we need, if there is the grass, we need to see it, and then we can say, this grass, yeah, for sure it's green, which means it will have a truth value of true. Or else you can say, this one is not what, it's not true, because the green is not what, the grass is not green. Also, you can have um Okay, so let's look at this one. We've got 4 plus 2 is equal to 6. This one we can say it's a statement. Why? Because it have got its own truth value is either true or false. And it's for this one, the truth value is false. Then we've got 4 plus 2 is equal to 7. So this one is also a what? It's also a statement. If we say there are 4 fingers in a hand, this one is also a statement, or we can say it's a proposition. It's also a proposition. Why? Because we can actually look at this one. If I've got 5 fingers, right? So I can actually say this one is wrong. So which means it's a proposition, but its truth value is false. But let's look at this one. If we say close the door, we cannot take this one as a proposition or take it as a statement, because it's like we are just commanding. We are saying close the door. Also, if what x is greater than 2, this one is not a proposition. Why? Because we do not know the value of x. It will become only a proposition if we substitute x with a value like maybe you can say 5 is greater than 2. That's when it become a statement. So this one, he is very rich. This one is not a proposition again, because we cannot determine if a person is rich. Why? Because we do not know, or we do not have the value or the best value for someone who is what, who is rich. So let's just look at this one. These are some of the example where you can understand that this is a statement. So guys, if you see proposition, it's just another name for a statement. Where you can just say this one is a statement, this was not a statement. If you say x plus 2 is positive, it's not a statement. Why? Because we don't know, we do not know the value of x. So you cannot know if it is positive. So may I come in? No, that one is a question. It's not a statement. Logic is interesting. This one is not a statement because you can quantify if it is interesting or not. It is hot today. We can tell, is it hot or not? If it is not hot, then we can say this statement is wrong or what, something like that. Minus 1 is greater than 0. It's a statement again, and with a truth value of what? Of false. X plus y is equal to 12. It's not a statement. So that's the difference between a statement and the one which is not a statement. So let's look at what we call a compound statement. Remember, we've said we've got a simple statement. Now it's a compound statement, which means we are joining more than one statement. So a compound or a composite statement is a statement which is comprised of simple terms and logical operations connectives. So a compound statement is denoted by use of letters P, Q, R. If you look at that, for simple, we are using the small letters P, Q, and R. For this compound statement, we are using this capital letter P, Q, and R. For example, here we are saying this capital letter P, which is there are 7 days in a week and 12 months in a year. If you look at that, we've got this statement and this statement, and we are joining them using the and connective. This is what we are using. So you can actually put this compound statement in its simpler term by saying that we've got this statement P, so that there are 7 days in a week, small letter P. Because this one is now a simple statement, and then Q, there are 12 months in a year, right? Excuse me, something like that. And we are using the operation and to join the two. Also, the grass is green or it is hot. We are using the or operation. If you look at it, the grass is green is a statement on its own, and then it is hot today is a statement on its own. So we're using or to join them to make a compound statement. So if you look at this one, we're saying it's Q or P. Sorry, I'm using a mouse, so it was going to be easy if I have a touch screen. It was going to be easy for me to write to just write using a pen or something else. But anyway, I'm trying to improvise with what I have. So if it is, we have got this P. If it is not raining, then I will go outside and eat my lunch. So if you look at this, we've got P, Q, and R. And if you look at this, if it is not raining, then I will go outside. So this one is a statement, this one is a statement, and then eat my lunch. So if you look at this, you can break it down in terms of PQR, where this is the negation of P positive. We are saying if it is not raining, which means if it is raining. So the negation is the opposite of that. So I'm saying if it is not raining, then I'll go outside and eat my lunch. And we are using, here we are using the if then connective as well as the end. We are going to talk about that later. We're going to talk about that later. So let's look at determine which of the following are simple statements and which are not. For those which are not, identify the simple statements used. So normally what we are saying here, this one we've got 2 plus 3 is equal to 4. It's a simple statement. It is hot and sunny outside. This one is not a simple statement, it's a compound statement with the P and the Q here, and we are using the AND operation here. For here, we are using the AND operation. 2 plus 3 is not equal to 6. This one is a simple statement. X is less than or equal to 2. It's not a simple statement. It's not a compound statement because you don't know the value of X. X greater than or equal to minus 5 and X less than 2 is not a simple statement, and it's not a compound statement. If I study hard, then I will pass my exam. This one is a compound statement, and we are using the if, we are using the implication. We call it the implication. You are going to see it later. We are using the implication. They're saying if implies, so you say P implies Q, something like that. You're going to talk about that. So let's look at this connectives, the connectives, which is this one, the conditional, which is the implication that I was talking about. So if you look at that, we've got the negation, which is the not. I can say it is hot today. That's the simple statement P. Then I will say it is not hot today. That's the negation of P. So that's what we call the negation, which is normally you can use this symbol. And then there's the conjunction, which is an and, which you've got any meaning of and you can use this symbol. And then you can, for oral operation, you can use this, which is looks like a V, this one. And there is the conditional, which is the if then. Then on if then you use the implication arrow, which means A determines B, or the implication A implies B, something like that, which is the conditional arrow. And then there's the biconditional arrow, where you have if and only if. For if and only if, it means that it can go both ways. If and only if, it can go both ways. Let's make sure that we are always on mute, unless if you want to say something. Unless if you want to say something. So for example, we can have P is equals to Harare is the capital city of Zimbabwe, and Q18 is divisible by 3. Then whenever you have P and Q, this one is a sign for what? For and. This one is a sign for and. So you're saying P and Q. It means Harare is capital of Zimbabwe and 18 is divisible by 3. Don't worry. If any of this, let's make sure that we are always on mute. Otherwise, let's make sure that we are always on mute. Let's all make sure that we're always on mute. Okay, so P and Q, it means that we are just joining this P and Q using the AND operation. And then if it is P or Q, we are joining these two using an OR. So Harare is the capital seat of Zimbabwe, is capital of Zimbabwe, or 18 is divisible by 3. And then the negation of P, it means we are negating this P. Let's say Harare is the capital of Zimbabwe, which means now it is not. So it is not the case that Harare is the capital of Zimbabwe. Or you can just simply say Harare is not the capital of Zimbabwe. That's the negation of what? Of P. So translation from English to symbols. So there might be a case where you'll be asked to translate from symbols to English, or from English to symbols. So you must be prepared and be ready to do that. So let P be equal to it is hot, and Q be equal to it is sun. So for these two simple statements, it is hot and it is sun. So if you look at that, if you are given this symbol, the negation of P, it means we are saying it is not hot as a sentence. So if you are translating from a sentence to a symbol, we are saying it is not hot, which means we are meaning the negation of P. And then if we say it is hot and the sun, it is hot is what? Is P. Sun, it is sun is what? Is Q. So when I say it is hot and the sun, it means we are saying P and Q. That's why I've got P and Q in terms of symbols. When I say it is hot or sun, it's P or Q. That's why I've got this P or Q. It is not hot, but sun. When I say it is not hot, which means we are saying the negation of P, because otherwise it is hot. So it is not hot is the negation of P. That's why I've got the negation of P. But it is sun, which means we are saying it is not hot and it is sun. That's why I've got and Q. Then when I say it is neither hot nor sun, it means we are negating both P and Q. So that's the negation of P and the negation of Q, because we are saying it is neither hot, which means it is not hot, nor sun, also it is not sun. So it's negation of P and the negation of Q, just like that. So example or practice, this is a practice when you have H, W, and S, then I say Donnie is health, Donnie is wealth, Donnie is wise, right? And then translate the compound statements to symbolic form. So you need to translate this English statement to its equivalent symbolic form. So how to do that? We are saying Donnie is health. If you look at that, you are talking about this H. That's why we've got this H. And which means that's why we've got this symbol. And wealth. After that, we are also but not wise, which means we are saying Donnie's health and wealth and not wise, which means the negation of S. That's why we've got this. And then Donnie is not wealth, but is health and wise, which means we need to negate this one, which is W. That's the negation of W. And H, which is his health, and also he is wise, just like this. So we say Donnie is neither health, wealth, nor wise. This is the negation of both H, W, and S, something like that. So translating from symbols to English, now you are given that Alex is good in mathematics and Alex is a computer science student. That's what you are given for M and C, right? So to translate the following statement from statement forms into plain English, like here, if you say the negation of C, it means that Alex is not a computer science student. Then if we say C or M, it means Alex is a computer science student or is good in math. If we say M and the negation, it means Alex is good in maths, but not a computer science student. So a convenient method for analyzing a compound statement is to make a truth table for it. So maybe you need to know how can you make a truth table for a given compound statement. So a statement P can hold one of two. So guys, I think this one is doable. I don't know if there are questions on this one. I think it's doable. Right? Is it doable? Sure, you can do this. So if there's total silence, it means everything is good. It means everything is good. So now let's look at our truth tables. A statement P can hold one of two truth values, which is either true or false. Either true or false. So these are denoted by T and F respectively. Some books may use 1 for true and 0 for false. Do not get confused if you saw that. So when determining the truth value of a compound statement, all possible combinations of the truth values of the statement comprising it must be considered. So this is done systematically by the use of the truth tables. Therefore, a truth table specifies the truth value of a compound proposition for all possible truth values of its constituents propositions. So let's look at how you can construct the truth table, because that's the first part of it. So to construct the truth table, assign each statement a column. That's the first thing. So if you have got three statements, if you've got a compound statement which is made up of three statements, what you need to do, you need to make sure that for P, for the first statement, you have got its own column, the second one you've got its own column, and then the third one you've got its own column, something like that. So the number of rows in the table is determined by the number of statements. So if you have any statements, it is obvious you're going to have 2 to the power n rows. So if you have got three statements, which means PQR, it means you are going to have 2 to the power 3 rows in your truth table, which is 2 to the power 3 is going to be what, 8. So systematically assign truth values to each of the statements beginning in the first column. So normally we use the half rule. So once all possible truth values for the simple statements are inserted, determine the truth values of the compound statements following the rules of the operations, right? So let's look at how can we create these truth tables. Let's look at how can we create these truth tables. So if P is a statement, so the negation of P is not P, right? The negation of P is not P, or it is not the case that P. Is it a contribution or a question? Let's make sure that you're always on mute, right? Let's make sure that you're always on mute. Okay. So it is not the case that P, that's what you call the negation. So if you are going to draw that truth table, the first thing is for P, you have got only one statement, which is P. So 2 to the power 1 is always true. So you're going to have 2 rows. That's why I've got this true and false, only these 2 rows. That's why you have only these 2 rows. And then you have got the negation of P as the result one, because this is the result that you want. So we are saying whenever you have got a true, and we are saying the negation of true is always false. So not true is obvious, it's false, and not false, it's obvious, it's true. So you are just negating this to get this, and then you negate that one, and you get this. So this is a truth table for the negation of P, or the negation of a statement. Then let's look at the conjunction and. Whenever you are given and you want to look at the truth table whenever you're using an and. So if P and Q are statements, then the conjunction of P and Q is P and Q, denoted as what? As this one, P and Q. So it is true when and only when both P and Q are true, and if either P or Q is false, or if both are false, P and Q is also what? Is false. So if you are looking at this truth table, so if you look at this, we are given a statement P and Q, and if you look at it, there are only 2 statements on it, right? We have P and Q, right? And we said that whenever you're drawing this truth table, if we are using 3 statements, 2 statements, whatever, the number of rows is determined by the number of statements involved. So the number of statements involved here, it's only 2. So it will be 2 to the power 2, it will be 4. So I'm going to have 4 rows, which means 1, 2, 3, 4 rows. And then when putting these values, we use what to call half rule. So here I've got 4 rows. So it's obvious we're going to start with the true, and then you put false. Or you can start with the false, and then you put it true. Whichever way you're going to do it is going to work. And then after that, for the second one now, you use the half of this one, which is now true and then false. If you come here, then true, false. So for the first one, you just put true, then false. And then for the second one, it will be true, false. Something like that. So if you are going to have 3, if you have 3 3 statements, it means that you're going to have 8 you're going to have 8 rows, which means maybe you're going to have true, 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 then false, false, false. And then for the second one, you have true, true, false, false, true, true, false, false. And then the other one need to be true, false, true, false, true, false, just like that. So that's how you create the truth table. And then let's look at this operation, the AND operation. You are saying P and Q. So when you, at this first row, we be say true and true. So if it is true and true, you're always going to get a true. But if it is true and false, you're always going to get a what? A false. False and true, you're always going to get a false. Then false and false is always what? False. And it ndizvo. Ukangotore something chiri true chibatanidzwa nenhema, it's obvious you are going to get nhema, handiti? Ungamixa nyangwe nyaya yako yanga ine musoro, handiti? But kana ukazongoimixa nezvekunyeba so, zvinobva zvaita zvekunyeba zvega zvega. So it is only true. So P and Q is only true whenever P and Q are true. That's what we are saying here. So it is true when and only when both P and Q are true. So that's what you need to know for the P and Q. Otherwise, it is false. So let's look at the disjunction or this one. It's just the same. We've got only P and Q. So we are going to have 4 rows. And then for the first one, we're going to put true, true, and then false, false, true, false, true, false. After that, if you look at that P and Q, sorry, P or Q, now it's now an OR. So we just need one of them to be true because we are using an OR. We are saying true or true, it means you're going to get a true. True or a false, you are going to get a true because we just need one of them to be true because we are using an OR. But otherwise, if it was going to be an AND, we wanted both of them to be what? To be true. So we're saying false and true, you're going to get a true. Then false and false, it's always what? Sorry, false or false, it's always a what? A false. Something like that. So this is how you solve this on this truth table. So if you look at this, it is only false when both are false. Otherwise, it is true. So it is true when at least one of P or Q is true and is false only when both P and Q are false. So you need to take note of this. And then exclusive disjunction, which is this one, exclusive disjunction. This one, we are no longer including those. Sorry, excuse me. You no longer include those which are at the boundary. That's why it's exclusive, or there is an exclusion there. There's an exclusion. So the exclusive disjunction of P and Q is symbolized as B by P. Then you put this sequence with a plus inside Q, which is exclusive disjunction. Which is exclusive, or we call it exclusive, or we can say exclusive disjunction. So it's P exclusive or Q, right? So if you look at this, we are no longer taking those which are at the what? At the boundary. So this compound proposition is true when exactly one, that is one or other, but not both of its components, is true. But true, sorry, is true. So the truth table for this one is this. If you look at this, for true exclusive or true, you are going to get a false, and then true exclusive, or you are going to get a true, and then false exclusive, true exclusive or true, you are going to get a true. So it is only true whenever you get the different inputs. Whenever you get the same inputs, it is going to give you a false. That's what you need to know on this one. So when two simple propositions are combined using OR context, you provide the clue as to whether the inclusion or exclusive sense is intended. Is this a question or a contribution? Let's make sure that we are always on mute. it will save us a lot of time. So for example, tomorrow I'll go swimming or play football seems to suggest that I will not do both, and before becomes and therefore becomes the exclusive or both. You're not going to do what you're not going to do both. So applicants for this post must be over 25 or have at least 3 years relevant experience. Suggests that applicants who satisfy both criteria would be considered, therefore, or becomes inclusive. So for the exclusive, you are just looking at one part. Uh, you are not including both, but for the inclusivity, we can either take both. So where context does not resolve the ambiguity surrounding the word or, the intended sense can be made clear by affixing or both to indicate the an inclusive reading. So, or by fixing a but not both to make clear exclusive sense. So where there is no clue as to which interpretation is intended and the context does not make this clear, then or is conventionally taken in its inclusive sense. And then let's look at the implication, which is if then. Let's look at the implication, which is the if then. So conditional if then or the implies statements. So whenever you have a conditional statement or the if then or the implies statement. So this one is also known as the implication. Consider the statement: if you earn an A in math, then I will buy you a computer. This statement is made up of two similar statements, which is P, you earn an A in maths, and Q, I will buy you a computer, just like that. So the original statement is then saying if P is true, then Q is true. Or more simply, if P, then Q. That's what it means. If you earn an A in mathematical foundation, then I will buy you a computer, right? So it means that for the second one to be true, the first one must be true. So that's the implication. So we can say it's the conditional if then, or we can say it's implied. So P implies Q, and we can write it as P with this forward arrow and then Q at the right hand side. So the conditional statements, if P and Q are statements variables, so the conditional Q by P is if then Q, or P implies Q and is denoted by this one. It is only false when P is true and Q is false. Whenever you have P as true and you have false here, it means it is going to be false, because there is no way that when I promised you that if you pass mathematics with an 8, then I'll buy you a computer. Then if I'm going to have a false on the Q side, it means that the whole thing is false. Otherwise, it is true. So the arrow, this one is the conditional operator. And in P implies Q, the statement P is called hypothesis. We call it the hypothesis. And the Q is called the what? The conclusion. So if you look at this truth table, we've got P and the Q, and the P implies Q. For drawing this one, I think I've explained on it. Let's look at whenever we've got true and the true, we're going to have a true here. Why? Because we are saying true implies true. But whenever if true implies false, it will become false, because remember I promised that if you do this, then you get this. So whenever you are saying P true, then and this one is false, it means that the whole thing is now false. Was it? If you really passed, you need to get something. You need to get, which means this one should be true. So this one become false. So false implies true, it will become true, and then false implies false again, it will become true. So to make sense out of it, true cannot imply false. Hakuna chokwadi chotipa manyebo adidi. So hakuna chokwadi chotipa manyebo, and so true cannot imply false. That's why we've got false here. but false can imply true. Sometimes you can say this is wrong, whatever, whatever, but you find out that no, this one is true later. So normally false can imply true. And also false implies false is always true. If you do not pass mathematics, it's obvious you are not going to get the gift, or you're not going to get the computer. So it's obvious it's true. So that's the truth table for P implies Q. Just need to master it. It's only false whenever you've got true implies false. Otherwise, it is always true. So you need to master that, so that whenever you are given maybe a compound statement, you can break that compound statement. Maybe that on that compound statement, there's a portion where there's P implies Q. So now you must be able to solve that. You must be able to solve that. So other ways of expressing the implications, you can have the implication P implies Q, which could be expressed in many alternative ways, which is if P then Q, or P implies Q, or not P unless Q. So you might be given a statement like this, and then it will be said, write it in simple terms. So you need to know that Q follows from P. It's just as good as P implies Q. If P Q, it means P implies Q. Q if P, it means P implies Q. P only if Q is just the same. Q whenever P, means P implies Q. P is sufficient for Q. Q is necessary for P, something like that. So more about conditional statements. Given the conditional proposition, P implies Q, can define the following. The converse, there's the issue of converse, inverse, and contrapositive. You need to know about this. If you say P implies Q, what is the converse of that statement? It means you are saying now Q implies P. That's the converse of it. Then the inverse is the same as we are negating both the P and the Q. So the negation of P will be implying the negation of Q. Then the contrapositive, you are saying the negation of Q implies the negation of P. You need to know this, guys. You need to know this. You need to know this. You need to know it. What is the converse of a given statement? What is the inverse of a given statement? What is the contrapositive of a given statement? You need to know it. So let's look at the truth table for the converse, inverse, and contrapositive. So if you look at this, we only have P and Q. That's why we've got only 4 rows, right? So we've got true, true, false, false, then true, false, true, false. Then we look at P implies Q. We've already done this. It is only false whenever we've got true implies false. That's why we've got only false here. Otherwise, it is true, true, true. Then for Q implies P, remember now we are looking at Q implies P. So it's now true implies true, yes. False implies true, yes. Then true implies false. It will become false here whenever true implies false, right? And then false implies false, it is true. Then for the negation of Q implies the negation of P. For you to be able to do this, you first need to negate this, and you need to negate this, and then you do the implication. Like if you look at this one, the negation of P implies negation of Q. You are looking at negation of T is false, and negation of this is false. So we are saying false implies false. That's why I've got a true here. Then here we are saying false implies true, because we are negating this true to false and this one to true. So whenever you have got false implies true, yes, we have got a true. Then whenever you've got true implies false, we have got a false here. And then true implies true, you are going to have a true. Then the negation of Q implies negation of P. You are coming from this side, going this side, but you need to negate everything here. So you negate this one to become false implies false. That's why I've got a true here. Then you are going to have a true implies false. That's why I've got a false here. Then you are going to have false implies true. That's why I've got a true. And then true implies true. That's why I've got this true. Something like that. So this is the converse, the inverse, and the contrapositive of a given conditional statement. You need to know that. You need to understand that. So there's this an exercise which says state the converse, inverse, and the contrapositive of the proposition. Like if we say if Jack plays his guitar, then Sarah will sing. For this given statement, it's an if then. So it's an implication. They are being asked to give the converse, the inverse, and the contrapositive. So what you need to understand is these definitions. What is the converse? The converse, you are just reversing to have Q implies P, right? And then for the inverse, you need to negate P and Q. So it's now the negation of P implies the negation of Q. And then for the contrapositive, just need to make sure that you swap and negate both. That's the contrapositive. So it's not the negation of Q implies the negation of P. Just like that. So that's what you need to understand. And then also this question says state the converse, inverse, and contrapositive of the proposition. If it's not hot, if it's not Sunday, then the supermarket is open at 2 midnight. So if you look at this, the first things first, you need to have P and Q as your simple statement, which is Jack plays his guitar and Sarah will sing. So that P implies Q, which is if Jack plays his guitar, then Sarah will sing. So if you want the converse statement, which is now you are swapping, which is Q now is implying P. You are saying if Sarah will sing, then Jack plays his guitar. So it's like they are changing their roles. Something like you are now saying this one is now implying this. And then the inverse of that is just P implies Q, but now you are negating both of the statements. You are negating which is Jack plays his guitar, which means not plays guitar. Then Sarah will not sing. And so that's what you're supposed to do. So if Jack doesn't play his guitar, then Sarah won't sing. As simple as that. Then the contrapositive, first you need to negate both and then you swap, which means the negation of Q9 implies the negation of what? Of P, which means if Sarah won't sing, then Jack doesn't play his guitar. Just need to know the inverse, contrapositive, and the converse of a given implication, just like that. So let's look at the inverse of conditional statements, how it will be like on the truth table. So I given P implies Q, and then the inverse is negation of P implies the negation of Q. So if you look at the truth table, we have got this one and this one. All right. So if you look at it, you want to compare this, we've got true, but if you look at here, we've got a false and we've got a true, here we've got a true and here we've got a false. So that's where they differ here. That's where they what? They differ. Otherwise, here it would be what? True, then here true. So if you look at this, what is happening here? True implies false, then you're going to have a false. False implies true, you're going to have a true. But here you're going to have true. Sorry, false implies true, then you have a true. True implies false, then you get a false. So that's how do they differ. They differ. They are not the same. So the inverse and the conditional statement itself, you're not going to get the same result. You're not going to get the same result. So let's look at the biconditional, which is the if and only if. So if P and Q are statements variables, the biconditional of P and Q is P if and only if Q, and is denoted by this double R, which is going forward and backward. So if and only if is abbreviated as IFF. So if we saw IFF, it means if and only if. So the double-headed arrow is the biconditional operator. So if we look at this, we've got P and Q, and then we have got P implies Q as well as Q implies P. So it's just like going both directions. So it is only true whenever you have got both true or both false. Otherwise, it is going to be false. Why? Because whenever you've got true implies false, it is supposed to be false, right? So it doesn't matter if false implies true, it's going to be true. Like here, false implies true, it's supposed to be true, but because it is also going back, true implies false. That's why we've got a false here. So you're going to get a false whenever you've got different inputs. Otherwise, it is going to be true. That's the biconditional. So a alternative wording, in terms of wording, how can you identify that? Here I need to use the biconditional rather than the conditional. like if you have got P if and only if Q, or a P if Q, or a P implies and is implied by Q, or a P is equivalent to Q, or a P is as necessary and sufficient condition for Q, something like that. Then order of operation for logic. This one is like what you have with the BODMAS, BOMDAS, something like that. So the order of logic, the order of operation for logic operators is as follows. If you are given a compound, you need to look at the evaluate negation first, then evaluate the or and end, then you follow the end. Second, when both are present, so evaluate V and end. Second, all right, so when both are present, parentheses may be needed, otherwise you work from the left going to the right, and then the implication, and this one third, which means this one will follow, and then the biconditional will follow last. So when both are present, parentheses may be needed, otherwise you just work from left to right. So use of parentheses will determine order of operations which override the above order. So in summary, you need to understand the statement, you need to understand how compound statements are formed, logical connectives, how to construct these, and then there's what you call a tautology. There's what you call a tautology. Um, there's what you call a tautology. You need to understand this. So a tautology is a statement from that is always true. Is a statement form that is always true regardless of the truth values of the statement variables. So a tautology is represented by the symbol T. So guys, in other words, a tautology is a statement that always give you a true in this column, and that's what we call a tautology. So the statement form P and or, so the P or the negation of P is always a tautology. Why? Because you always get this as true. Then there's what you call a contradiction, which is almost like the opposite of tautology. So a contradiction is a statement form that is always false, regardless of the truth values of the statement variables. So a contradiction is represented by the symbol C. So if we have to prove that a given statement form is contradiction, we will make the truth table for the statement form. And if in the column of the given statement form, all the entries are F, then we say that the statement form is contradiction. That's how you can prove. Even for the tautology, you do the same. And then if they are both true, you can say that this is a tautology. So the statement form P and the negation of P is a contradiction. Why? Because you always get these false, just like that. So since the last column in the truth table, we have F in all the entries, so is a contradiction P and the negation of P, just like that. So you identical to C. So these are some of the remarks. So most statements are neither tautologies nor contradiction. So a proposition that is neither a tautology nor a contradiction is called a contingence. We call it a contingence. So the negation of a tautology is contradiction and vice versa, which means if it is a tautology, if you negate it, it will become a contradiction. In common usage, we sometimes say that two statements are contradictory. So by this, we mean that their conjunction is contradiction. They cannot be both true. Then there's what we call logical equivalence. You need to understand this one as well. So two compound propositions are called logical equivalent if and only if they have the same truth values, no matter what truth value their constituent proposition they have. So we can say that they are logical equivalent. For instance, P implies Q and negation of P or Q are logically equivalent, and we write that this one is the one that we use this symbol for logical equivalence. Not that if two propositions P and Q are logically equivalent, then P implies Q and Q implies P. This one, the if and only if or the biconditional is a tautology. So determine if two statements P and Q are logically equivalent. Construct a full truth table for each statement. If their truth values are the truth value at the main connective are identical, the statements are equivalent. So in other words, if you need to do the truth table for this and you do the truth table for this, or you can do them at the same truth table, and then you look for this column, for these columns, these two columns. If they are the same, you can say they are logically equivalent. That's what we are saying. For example, P implies Q, and the negation of P or Q, they're at the same truth table. And if you look, our critical columns are these ones, these two. And you need to look if they are the same. If you look at it, they are what? They are same for every end. Then we can say that they are logically equivalent. So that's how you can prove if they are logically equivalent. So take note of that so that it won't be that much difficult. And then there are some examples and some practice. So for laws of logic, we are not going to do this. Maybe we are going to do it when you are doing discrete mathematics. When we are doing discrete mathematics. But for today, that's all what I wanted us to cover. For now, maybe I can take questions if there are questions, as well as contributions if there are contributions. I've talked too much. So guys, do you have questions? It's like people do not want to ask. I think I've done a good job.
Yeah, I've got no questions, sir.
Okay, what about maybe some additions or those that want to put some contribution? Never know. Okay, so let me stop my recording. Mm.